Class recording has started. So, on Friday, we introduced our next topic, that being impulse momentum equation. And we said that the idea of impulse momentum comes from an old equation that we used in the last chapter. And that old equation was what? Newton's second law, right? Sigma F equals m times a. And we said the one thing that this equation maybe didn't tell us about was the fact that acceleration actually depends on two things, right? What are the two things that we said acceleration depends on? Time and change in velocity, right? So we can rewrite this equation to look like this, where we now include both the change in velocity and the change in time factor. We do a little rearranging of this equation, and we end up with this. And we said that that equation we refer to as the impulse momentum equation. Okay? This side of the equation we said was the impulse side. Okay? We said, what is our definition of impulse? How did we define impulse or explain impulse? What does impulse do for us? Causes a change in an object's momentum, which means that over here, this has to be change in momentum. Because earlier in the period, we defined momentum as mass times velocity. That would be the object's instantaneous momentum. So instantaneous momentum, P is equal to m times v, mass times velocity. But if we want to change the momentum of the object, now we have to apply an impulse, which leads us to the force times time. That causes the change in momentum. Right. Good there? All right. A couple of questions. Get us started for today. So, first question. First question says, a truck with a mass of 5,000 kilograms is traveling on a road with a speed of 25 meters per second. An identical truck is traveling on a highway at 35 meters per second. Which truck has a greater momentum? So in this case, I've learned last period lots of spelling errors today, so good. It's like the road Truck, or the highway truck. So, which of these two objects would you believe has the greater momentum? Greater momentum. Road truck or highway truck? Results are pouring. Give it another second here. 12. In there. 2 people absent. All right. So we are in agreement that the highway truck has a greater Someone did that on purpose, didn't they? All right. We are in almost unanimous agreement that the highway truck has a greater momentum than the road truck. And that is the case, right? We said that the instantaneous momentum of an object depends on both its mass and its velocity. Two trucks with the same mass, one traveling faster than the other, that one has the greater momentum. Good there? All right. Next question. Next question says, a truck with a mass of 5,000 kilograms, is traveling north on a road at a speed of 25 meters per second. An identical truck is traveling south on the same road at 25 meters per second. At the moment they pass each other, which statement is true? So, northbound truck has more momentum, southbound truck has more momentum, they have the same momentum, or none of these are true. Which of these statements best describes the situation as they pass each other? Northbound truck has more momentum, southbound truck has more momentum, they have the same momentum, or none of those statements are actually true. Check out our results. Okay. Correct answer is that none of those statements are actually true. Okay? The reason being, what did we say about momentum on Friday? It is a vector quantity. Momentum is a vector quantity. So, they have the same magnitude of momentum, but because their directions are different, they have a different momentum. Okay? Tricky, but we got to keep that in mind, especially when we start looking at conservation of momentum, which we'll get into a little bit more tomorrow. Okay? Momentum is a vector, so it has direction. Good there? All right. Next question. Says a truck with a mass of 5,000 kilograms traveling on a road at a constant speed of 25 meters per second. An identical truck is traveling on a highway at a constant speed of 35 meters per second. Which statement is true? So first statement, road truck has a greater impulse. Second statement, highway truck has a greater impulse. Third statement, they both have the same impulse. Fourth statement, neither has impulse. Fifth statement, none of those statements are true. Two trucks, equal mass, one constant speed of 25 meters per second, the other constant speed of 35 meters per second. This time asking you about impulse. Take a look. Suspense is killing me. All right. Correct answer is, going back to our definitions, what did we say that impulse does? Causes a change in momentum. But what does it tell you about both of these trucks? They're both moving at a constant speed. are their momentums changing at this point in time? No. So that means that the correct answer for this question would be that neither one of them has impulse, because there is no change in momentum. Okay? Tricky, but got to keep our definition straight. Okay? Are we okay with that one? All right? Okay. With that being said, let's go our last question. Last question to start us off here, and that will get us into the next part. Says, trapeze artists will use a net during their performance, probably to prevent little kids from the horror of witnessing them fall. The net prevents them from being injured when they fall. Dot. Extra dot. So, which of the following is the best description of why? So 3 choices. The net cushions their fall. 2, the net provides a greater force to stop them more quickly before they hit the ground. Or 3, the net increases the amount of time to stop them, which requires less force. On the right track on this one, okay? This problem, this question, is similar to these 2 pictures of the egg, right? Did I show you the egg pictures on Friday or no?
Yeah.
Okay, I couldn't remember if we saw these ones or not, but yeah. So, I just cut off the egg picture, but funny. That was a call slip for Tom Kellerman. Obviously. All right. So there's my egg picture. Okay. In both cases, right, we drop the egg from the same height. By the time it reaches the ground, what can we say about how fast it's going? If we drop the egg from the same height in both cases. Maybe not that fast, but it's going to be going, they'll be going the same speed, right? Because if we drop those 2 things, they fall next to each other, blah, blah, blah. Okay? But, in this case, what has to happen to both of these eggs? They both have to what? They both have to stop, right? So we kind of talked about on Friday that in using impulse momentum, sigma F, delta T, M delta V, a lot of times in the case of stopping, this side of the equation is the same, no matter how we do it, right? Here, that leaves us then with what kind of relationship between force and time? If the right-hand side of this equation is the same, force and time will have an inverse relationship. Okay? The egg actually increases the time it takes, or sorry, the pillow increases the time it takes for the egg to stop. If it's a bigger time, how much force is required? Less force. Okay? Good there? If you flip over to the back side of the page that I gave you today, oh, by the way, as far as that poll question goes, this was the right answer. The net increases the amount of time it takes for them to stop, therefore less force. If you go back to the back side of the paper that I gave you today. Questions 12 through 14 deal with that concept mathematically. So, it says an SUV with a mass of 2,200 kilograms is traveling at 94 kilometers per hour, which is converted 26.11 meters per second. Question number 12 says, applying the brakes gently, the vehicle comes to a stop in 21 seconds. How much force is applied to the SUV by the brakes in this instance? So, what is question number 12 asking us for? Force, right? So, question number 12, forces are unknown. Okay? Things they tell us in this case. Okay? Let's go with the problem. Let's go with the problem first. So, in problem, what's the first other piece of information they gave you in number 12? Okay? They gave us the time. You'll see that that's really just for me to be convenient when we go onwards. So other things that they told us about this. They gave us the mass of the SUV, right? They told us. They give us a velocity. Which velocity is that going to be? That's going to be the initial velocity, because Olivia, what does it say happens in the problem? It stops, right? So it tells us that the initial velocity is going to be 26.11 meters per second, but then the final velocity is going to be 0. Okay? Good there? All right. Based on this information, we now have enough stuff that we can plug into our impulse momentum equation and solve for what we need to solve for, right? Sigma F, delta T, M, delta V. Okay. So we start plugging things in. First, do we know the force? We do not. That's what we're looking for. They gave us the time in this case, 21 seconds. That then equals the mass of that SUV, 2,200 kilograms, times delta V. Right? Important that we keep track of stuff here. How do we calculate delta something? When we calculate delta anything, it's always final minus initial, right? Delta whatever is always that final minus initial, or 2 minus 1, right? What's the final velocity here? 0 minus the initial velocity, which was 21 or 26.11 meters per second. All right, let me pull out the calculator and figure out what the force that needs to be applied to this SUV to bring it to a stop in 21 seconds. Anyone got an answer for me?
-2735.3.
Good there? So first, too many sig digs, but let's not worry about that right now. Okay? Second, does it make sense that this force comes out to be negative? Roxanne says yes, she's right. What's happening in this problem? It's slowing down, right? So which way do we have to apply the force in order to get something to slow down? In the opposite direction. Good there. If we take a look at number 13, 13 says that the SUV slams on the brakes and comes to a stop in 3.5 seconds. How much force is applied to the SUV in this instance? Still, in number 13, what are we looking for? Still looking for force. But now, it tells you what about the time? It's 3.5 seconds instead of 21 seconds. But, does any of the mass or velocity information change? Still the same SUV, so it's still the same mass. It still tells us that it's starting off at 26.11 meters per second and coming to a stop. It's just slamming on the brakes instead. So now, let's rearrange this equation, not rearrange, but recalculate this equation, plugging in 3.5 seconds for the time instead of 21 seconds for the time. And when you do that, so when you do that, force, what do we get here?
Negative 22,976.8.
Good there? Just to finish it off, in number 14, right now, no brakes at all. Okay? Hitting the brick wall in a head-on collision, the SUV comes to a stop now in 0.22 seconds. Okay? But does any of the information, mass or velocity-wise, change? It's still the same SUV, and it was still going 26.11 meters per second, and it's still ending up at 0. So that means that the right-hand side of that equation is going to stay exactly the same. The only thing that's going to change now is that the time is now 0.22 seconds instead of 21 or 3.5.
How would she do that?
I think it's negative 16,400. It's not like, yeah.
Sounds better, actually.
Yeah.
Sorry.
Alright.
This can stop me. I think it is around 16,000. Is
16,405.
that better?
Yeah.
Sorry. All right, but now the flow is totally ruined. You know. All right, so sit. I know. We might as well just pack it. Sure. All right. So in this case, number 14, right? The information on mass and velocity is going to stay exactly the same. The only thing that changes now is the time. Everybody's going to be scared to give their answer. Is it like 220,000, something like that?
61,100.
261,100. So we see here, right, in all three instances, what's the end result of the impulse that we provide to the car or the SUV? In all three cases, what happens? It stops, right? But, sorry, go ahead. But, that was the next step, right? But now, in all three cases, it stops, but what do we see happening in each case? Force gets increased, right? But it's applied for a shorter time, right? So we have that inverse relationship between force and time if the end result is the same. And a lot of time, that happens when we're stopping.
Wait, what's the order of like the answers?
So
I don't get it. Oh.
I tried to keep them in color too. Yeah. So, yeah, 13 is going to be the blue colors, Emily. So like the 3.5 for the time, and then that's going to be the value for the force, and then the purple 0.22 for the time, and a much bigger force.
Okay. Thanks.
All right, good there. But something that I don't want you guys to fall into the trap of. Force and time are not always inversely related. Okay? That only happens if the change in momentum is the same no matter what. Like a lot of times in the case of stopping, that's the case. But if you flip it over to the front side of that problem set, questions number 6 and 7 deal with speed skating, which nobody ever really pays attention to unless it's, you know, the Winter Olympics, pretty much. But back in 1998, the Winter Olympics in Nagano, Japan, speed skating was revolutionized. I mean, you're the person who revolutionized speed skating. I don't know really where that puts you in the hierarchy of revolutionary people, but, you know, whatever. So, the people in the Olympics, the Olympic Committee, allowed the speed skaters to start wearing different kinds of skates. And as you can see from the picture up in the top left up here, that these skates actually have a little hinge on the toe, but the back part of the blade is actually not attached to the skate itself. So, as you can see from the bottom picture, when they go to push off of the ice, right, the back of the blade actually comes apart from the boot for a little bit, but then when they lift their foot off of the ice, it snaps back into place. And it makes a little clapping sound, so they're generally referred to as clap skates. Okay? But if we go back to our equation, right, our impulse momentum equation, why is this helping us? What's going on here? So 1998, the first Olympics that they allow these skaters to use these skates, and like every world record or an Olympic record got broken at those Olympics. Any suggestions why? No. You didn't have, that was fake insight. Well, let's take a look at this equation, right? There's my impulse momentum equation. Okay. If I'm interested in breaking world records in speed skating, which part of this equation do I need to affect the most? That part, right? Because what's that? That's how fast I'm going. Okay? If I'm going to break world records in speed skating, I need to make my change in velocity as big as possible, because that's going to get me going as fast as possible, and that allows me to achieve my lifelong dream of setting records in speed skating. Okay? If your name is Klaus or Jan or some other guy in Norway, that's probably is your dream. The Netherlands as well. I guess the Netherlands are big speed skating guys. So. Canada too. But if I want to make delta V as big as I can, what am I going to do with the rest of my equation? Delta V is on which side of that equation? The right-hand side. If I want to make the right-hand side as big as I can, what do I have to do with the left-hand side? I got to make, if I want to make this whole side of the equation big, what do I got to do over here? I got to make this big too, right? Because it's an equation. The two sides have to be the same. Okay? In the problem we were just doing, the right-hand side stayed exactly the same. So F and T we can mess around with. But here we want to make the whole right-hand side of this equation as big as possible. So what do I do with these two things? If I want to make this as big as possible, I want to make these both as big as possible. Okay? Force comes from how strong you are. Did people just miraculously get stronger at the 1998 Winter Olympics? No. Okay? But where does the force come from when you're walking or speed skating or doing any other motion thing? The ground. The ground, right? You push on the ground and it pushes back on you. Okay? Yes? Okay. When you jump really, really high, or you try to jump really, really high, right? You bend your knees, and then you push up like this. By bending your knees, what are you doing to the amount of time that you are in contact with the ground? You're increasing it. What do those those skates allow the person to do?
On the ground longer.
Stay on the ground longer. And if the skate is touching the ice longer, what is the ice doing longer to that person? Pushing them, right? So you work out and you make the force that you apply to the ice as big as you can. But then you wear your clap skates, and now you're applying that force for an even longer amount of time. If that's the case, what's going to happen to your change in velocity with each stroke? It's going to go up. And if your change in velocity is bigger, now you've become the Olympic champion. Okay. All right, good with that? That basically answers number 6. Okay. But, to close this up for today, I would like you to do one thing for me. This paragraph right here is a paragraph that I got off the internet explaining clap skates. But there is something wrong with that paragraph. I would like you to read this paragraph and then talk to the person that's in front of you, behind you, next to you, whatever, and see if you guys can determine what is wrong with that paragraph. One piece of inaccurate information. So read that paragraph. There it describes clap skates, and then there's something that's not right in there. Go ahead and do that, please. So, let's wrap this up. So, what's the piece of inaccurate wording they have put in here? What is the phrase that needs to change?
Increasing the skater's pushing power.
Increasing the skater's pushing power, right? Does it actually increase how hard the person is pushing on the ice? No. Right? That's not what it does. What it does increase the amount of time that that object is pushing on the ice, and the person is pushing on the ice. The end result is the same. You still end up with a greater increase in velocity, just a different way of going about doing it. Okay? Good there? All right. For tonight, on the calendar, there are some practice problems dealing with some calculations, impulse momentum-wise. Okay? Also, on the homework section, there is a link that says problem set answers. You'll find all the answers to that problem set that I just gave you today. Okay? Also, if you have not done your calculations or your questions relating to the lab from last week, the impulse momentum lab that we collected data for on the 7th, you have the information that you need to answer those questions and do those calculations now. Like I said at the beginning, I'll give you a little bit of time at the beginning of class tomorrow, but I do want to move on to some new stuff towards the end of class tomorrow. Yes, Kate? Yeah, I agree. I'll give it to you right now.